Okay, guys, we're back. Looking at the new material for this week. So we're moving on to chapter 14. Chapter 14 is a long chapter. Hold on a minute, I'm checking something. Yeah, okay. It's a long chapter with a lot of materials, so I think we're going to spread chapter 14 out over 3 weeks instead of our usual 2 weeks. We're doing distance learning, a lot of new material, a lot of stuff going on in the world, so we're just going to try to slow it down just a bit. So hopefully that will be relieving to you. So chapter 14 is on thermodynamics. So again, we're still going to be studying heat and energy. The word thermo hopefully gives you a clue to that. And the chapter starts out talking about that, we've been talking about all these chemical reactions all year, like they just happen. And there are a lot of reactions that happen with no outside help. So we talked about like the galvanic cell. That reaction is going to happen as soon as the reactants meet up with each other. And when a reaction just happens like that, it's called a spontaneous reaction. Okay? So as soon as the reactants come in contact with each other, the reaction happens. Okay? But there are some reactions that are not spontaneous. Okay? So you could mix the reactants together and nothing happens until they get a little outside help. And maybe that help is, we add electricity to the system or we add a catalyst, which we'll talk about later. But not all reactions are spontaneous. Several reactions, a lot of reactions do just happen as soon as the reactants come in contact with each other, but sometimes not. Okay, so all of this brings us to a concept called enthalpy. Okay, and enthalpy, for some reason, is abbreviated with a capital H. Okay, this enthalpy helps us understand the energy that's involved in chemical reactions. Okay, so enthalpy helps us understand the energy involved in reactions, in chemical reactions. And enthalpy is actually a measure of the system's potential energy. Okay, so remember, enthalpy is a measure of the system's potential energy. Okay, now enthalpy is really difficult to measure directly, but when a chemical or a physical change happens, the change in enthalpy can be measured. So we talk about enthalpy, but actually what we use is the change in enthalpy. This is what we use in our analysis, okay? So the change in enthalpy then is the energy change that results from a chemical or physical change. Okay, and usually this change is measured in joules per mole, or even more commonly in kilojoules per mole. Okay, so let's think about this a little bit more. At the very end of the last chapter, chapter 13, we talked about exothermic and endothermic reactions. Okay, exothermic heat is being released, endothermic heat is being absorbed. So in an exothermic reaction, we have potential energy that's converted to kinetic energy. Okay, a lot of times the example they'll use here is like a fire burning. Okay, there's potential energy in the wood, and as it burns, it releases energy that we feel as heat. So the potential energy is becoming kinetic energy. Well, in these kind of equations, obviously we're losing potential energy. Potential energy is being converted to kinetic energy. So we're losing potential energy. Okay? And when we lose potential energy, that means we're going from a high amount of enthalpy to a lower amount of enthalpy. Because remember, enthalpy is potential energy. Okay? So we're going from a high amount of potential energy to a lower amount of potential energy. Therefore, our change in enthalpy will always be negative. Okay? In an endothermic reaction, everything is the opposite. We have kinetic energy that's being converted to potential energy. So we're gaining potential energy. Okay? And when we gain potential energy, that means our change in enthalpy will be positive. Okay? So hopefully that's making some sense. Enthalpy is a measurement of a system's potential energy. In an exothermic reaction, we're losing potential energy. The potential energy is being converted to kinetic energy. So we're losing potential energy, and because we're ending up with less potential energy, our change in enthalpy is negative. In an endothermic reaction, kinetic energy is being converted to potential energy, so we are gaining potential energy. So our change in enthalpy will be positive. Okay? Calorimetry can be used to measure this change in delta H. Hold on here, let me review something. So there's an experiment in the book that we won't be able to do because neither you nor I have the proper supplies. But in the book, in experiment 14.1, they take sodium hydroxide, which is a solid, and they add to that vinegar. Which of course is an aqueous solution, and that produces water, liquid, plus NaC2H3O2, which is an aqueous solution. Okay, so we have this chemical equation going on here. So we do this in the calorimeter we add the vinegar to the calorimeter. So instead of water, our liquid in the calorimeter is the vinegar, and we measure its temperature. Then we slowly add this solid sodium hydroxide to the calorimeter, and we let these two react. At the end, we measure the final temperature. The final temperature would have increased. It would have gained heat. So where did that heat come from? This equation, we gained heat, so where did that heat come from? Well, it came from the chemical reaction. So the chemical reaction, then we know, is exothermic. Because if these two things were in the calorimeter, the temperature would go up. So to calculate the delta H for this, we use the mass for the sodium hydroxide. We convert that to the number of moles. We know how to do that using the periodic table. And then we divide the heat that we have by the number of moles. Okay? And that would give us delta H, because remember, delta H is measured in joules per mole, heat per mole. Okay? So most reactions like this, they actually release or absorb thousands of joules per mole. So really this kilojoule per mole is used more commonly. Okay, so we won't be able to do experiment 14.1. But hopefully that gives you an idea of what happens. Read through it in your book, read through what happens, and hopefully you can picture what's happening even without doing it yourself. There aren't specific comprehension check questions or review questions about this experiment, but you have to kind of understand the concepts behind it. And if you understand this, you'll be doing well. Okay? So I guess some of the key things: enthalpy, it's a measure of potential energy, and to understand these two lines. Read the book, and that will help reinforce it. Okay, so remember now, as I've said many times, enthalpy measures the potential energy. But where does that potential energy come from? And I mentioned it in our review, but the potential energy in chemistry comes from chemical bonds. So those bonds are storing up energy that can be released. So let's look at this a little bit more carefully. So let's look at this chemical equation. 2 hydrogen molecules plus oxygen yields 2 water molecules. Okay, this is actually a type of combustion formula, so hopefully you remember that. When we add pure oxygen to something and end up with water, it's combustion. It's the combustion of hydrogen. Okay, and a combustion reaction, we know, is exothermic. It's going to release heat. Again, if it releases heat, that means potential energy is being converted to kinetic energy. So we're losing potential energy, and therefore our delta H will be negative. Okay, so let's look at what's really happening here though in terms of the bonds. Okay, so if you remember back to our Lewis structure, if we would rewrite this chemical equation in terms of bonds, like with the Lewis structure, we'd end up with something that looks like this. 2 hydrogen molecules, or I'm sorry, 2 hydrogen atoms with a single bond between them. And there's 2 of these, so we'd have another one. Okay, then we would have our O2 molecule, and if we did the Lewis structure for that, it would look like this. Oh, sorry, I was going to do my bonds in red. Okay, so this 2H2 is here. Here's our 2H2 molecules. Our 1O2 molecule, when we do the Lewis structure, we would end up with this. We would have 2 oxygen atoms with a double bond between them. And that would yield 2 water molecules. That look like this. So this is bringing back Lewis diagrams from before. So refresh your memory about how to do those. So we would have 2 water molecules. That's what's indicated by the coefficient 2 here. Both water molecules have an O with two H's attached with a single bond. Okay, so when we look at that, when we look at what needs to happen to go from here to here, what happens is this bond needs to be broken. This bond needs to be broken. This bond needs to be broken. So all these bonds of the reactants need to be broken. And then to make our water molecule, these two bonds need to be formed. And these two bonds need to be formed. So the bonds in our reactants need to break apart. The individual atoms rearrange themselves and new bonds need to be formed. So here 3 bonds are being broken. 1, 2, 3, 4 bonds are being formed. Okay, so the reactant bonds must be broken and the product bonds must be formed. Okay, now to break a bond, we have to use energy. Okay, to form a bond, we actually release energy. Okay, these molecules are very happy like they are. They're very stable. The H2, the O2 are happy. So we have to use energy because we're actually taking them from a stable state to an unstable state, and that requires energy. To form the water then, these individual atoms are forming into more stable molecules. So we release energy because the molecules are becoming more stable. Okay, so when we break the bonds, we use up energy. When we form bonds, we actually release energy. Okay, so to calculate the change in energy then from our reactants reacting to new products being formed, what we do to calculate that change in enthalpy is we take all the energy that's required to break the bonds of the reactants, and we subtract the energy required to create the bonds of the products. Okay, so to calculate our change in enthalpy, we take all the energy required to break these bonds and subtract all the energy required to form these bonds. Okay, so if it takes more energy to break than create, so if it takes more energy, so let's say energy to break is greater than energy to form, then we are going to have an endothermic reaction, and delta H will be positive. Okay, and then likewise, if it takes more energy to form the bonds is greater than the energy to break the bonds, we will have an exothermic reaction, and delta H will be negative. Okay, so let that form let that sink in a little bit. So if the energy here to break the bonds is greater than the energy here, so this number is greater than this number, our delta H will be positive, and it's an endothermic reaction. If the energy here is less than the energy here, mathematically our delta H will be negative, and we will have an exothermic reaction. Okay, so then that begs the question, how do we determine these energies required? How do we know how much energy is required to break these bonds? And how do we know how much energy is required to form these bonds? Well, actually, you'll be glad to know this. These are already measured for us. So if you look at page 420 in your book, you will see a table of bond energies at the bottom, okay? And these bond energy is what's required to break a mole of a given type of bond. So the larger the number, the more energy that's required to break the bond. If it takes a lot of energy to break the bond, it means that it was a really strong bond. Notice, maybe I could move my book here. Okay, so here's the table we're looking at. Notice these double and triple bonds down here. All of these double and triple bonds take a lot more energy per mole than any single bond. So for instance, it looks like the greatest energy required to break a single bond is this bond between H and O. A single bond between a hydrogen and an oxygen atom would require 460 kilojoules per mole of this molecule to break that bond. So 460 is the greatest single amount of energy we have, and it is less than the least double bond. So double bond between our oxygen molecules takes 498 kilojoules per mole. Look at these triple bonds. They take a lot more energy. We know it's a triple bond because of these three lines between. They take a lot of energy to break these bonds. And it kind of makes intuitive sense. It would be harder to break a triple bond than a single bond. Okay. Another thing I want you to notice is that, like, if you look at CCl here, it takes 330 kilojoules per mole to break this bond. This could also be written Cl-C. This just indicates a bond between a carbon and a chlorine atom. Okay, it can be written either way. Either way it's written, this bond between carbon and chlorine, or between chlorine and carbon, whichever way you write it, takes 330 kilojoules per mole. Okay, so let's go back to our paper here. So let's take this same equation. Let's see if I can fold this paper down a little bit here. And see if we can figure out what is our delta H numerically for this reaction. Okay, so I'm looking at, example 14.1 on page 421. So it wants to know what is the delta H of this reaction. Okay, so remember, our delta H equals all the energy to break bonds, and I subtract all the energy to form bonds. And I'm breaking bonds in the reactants, and I'm forming the bonds of my products. Okay. So if I just look at my reactants first, okay, I have 3 bonds that I need to break. I need to break an HH, I need to break this HH, and I need to break my double bond between my oxygen molecule or atoms. Okay, so how much energy is required to break a single hydrogen bonded to a single hydrogen? If I look on page 420, I can see that that takes 436 kilojoules per mole. Okay, this one likewise would take 436 kilojoules per mole, and my double bond between my oxygen is 498 kilojoule per mole. Okay. Now the way I have this written, this is 1 mole, this is 1 mole, this is 1 mole, this is 1 mole, and this is 1 mole. So all of these are times 1 mole. Okay, so my mole cancels out and I'm left with kilojoule. So if I add all these up for my reactants, I have 1,370 kilojoules. That's how much energy is required to break these 3 bonds. Okay. On my products, I have 2 water molecules. So another way to calculate this is to say I have 2 moles of my water molecules. Sorry, I don't have, let's look at this differently. I actually have 4 bonds that I need to form, okay? Or that I need to form. So I need to form 4 single bonds, all like that, okay? So each OH single bond, if I look on my table, is 460. If I add that up, I have 1840 kilojoules, okay? So my delta H then I'm sorry. Forget what I said up here about moles. I'm getting ahead of myself. So we're just coming up with delta H, which is in kilojoule per mole. So hopefully this hasn't thrown you off too much. My reactants, I have 3 bonds that I need to break. Those are my 3 values. My products, I have 4 bonds that I need to form. These are my 4 values. I add them up. So my delta H then, I take my bond energy for the reactants, which is 1370 kilojoule per mole, and I subtract my bond energy of my products, which is 1840 kilojoule per mole. And if I do that, I end up with negative 470 kilojoule per mole. Okay, now does this make sense? This negative implies that I have less potential energy than what I started with, which indicates that it's an exothermic reaction. Okay, so all I did to figure out my delta H was I looked at all of the bonds in my reactants and how much energy it would take to break those. Then I looked at all of the bonds in my products and how much energy it would use to create those. I subtract my products from my reactants, I ended up with a negative delta H, which tells me this is an exothermic reaction. Okay. That's all. Example 14.1. Okay. I want to look at this example a little bit further because I think I've confused something and I don't want you guys to walk away confused. So another way to look at this is to look at the initial reaction. Okay, we had 2OH plus O2 yields 2H2O. I have 2 moles of my H bonds. I have 1 mole of my oxygen bonds, and I have 2 moles of, I have 4 moles of these water bonds, because each of these has 2 bonds times the 2 is 4. So another way to calculate my delta H, which is how the book shows it, is I have 2 moles of these H bonds, which are the 436 kilojoule per mole. Okay, then I have 1 mole of my oxygen bonds, which is the 498 kilojoule per mole. And I want to subtract then 4 moles, because each water molecule has 2 bonds, and there's 2 of those molecules, so 2 times 2 is 4 of the 460 kilojoule per mole. Okay, and here the moles cancel out. So actually, I'm sorry, I did get confused. My delta H, I should be measuring in kilojoules. Okay, and if you do the math out, you get the same answer. Okay, so here we were just looking at it. Each of these was 1, so we didn't have to do any multiplication. I could have done this, since we were doing it 4 times, I could have just done 1 of these times 4. Here are my 2, so there's where my 2 moles come in. This is my single, so this is 1 mole. All right, so hopefully that cleared that up. Okay, so now all what we've discussed is good, but it didn't take into consideration the phase of the chemical. And the phase affects how much potential energy a chemical has, and because it affects the potential energy, it therefore also affects the delta H. So it would be good if, when we were finding these delta H's, if we took the phase of all the chemicals into account. Okay, so we started out very simply and we didn't pay attention to the phase. Now we are going to take the phase into account. Okay. The book talks about we can do this and take this phase into account because enthalpy is a state function. And it talks about this state function. And a state function just means that the enthalpy depends only on the current state and not how the system came to be at that state. Okay, so it uses an example in the book on page 423 of kind of explaining what a state function is. It shows this picture on page 423. It shows point A down here at the base of a mountain and point B being at the top of the mountain. And it's saying the altitude of A and the altitude of B is a state function because it's a property that's independent of how we go from point A to point B. So it uses the example, we could take the smooth, windy road and start at A and go all the way to B. And we would cover a lot of distance. We wouldn't have to work very hard because the road is smooth and we would end up at B. Alternatively, we could start at A and we could climb this mountain. Forget the road, we're going to climb the mountain and go directly to B. So the path would obviously be shorter, but it would probably take a lot more work and energy to get there because this is rugged terrain, there's no road, who knows what we would encounter along the way. But either way, when we go from point A and we end up at B, we're still the same distance, the same height above sea level. So it didn't matter if we went on the road or if we hiked up the mountain. We ended up at B, and B, the altitude of B, is a state property or a state function because it doesn't matter how we got there. All that matters is that we're now at this altitude. Okay? So I've underlined down here, when you get to point B and measure how high above sea level you are, will it be different if you traveled the road compared to if you went straight from A to B? Of course not. Regardless of how you got to B, once you're there, your altitude is the same. It doesn't depend on the path you travel. So altitude is a state function. Okay? So in the same way, our delta H and enthalpy is a state function. It doesn't matter how we get to where we get, but we can measure enthalpy at the current state. Okay, so I just wanted to go through that example and explain that picture. Okay, so what does all this mean when it comes to chemistry? Okay, so we could look at the following chemical reaction. CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O. And this is a gas, okay? So we could look at the delta H of this reaction the same way we did previously in the previous example. And we could break down all the reactants here, or all the bonds here. We could break down all the bonds here. Then we could figure out what bonds were here and form them, and we could figure out what bonds are here and form them. So we could do it like we did before, and then just use the individual atoms to form the products. But that might seem like a lot of work because the delta H's of, so that would be a lot of work. So there's a little bit of a shortcut that we can take because the delta H's of many of these formations are already known. Okay, so without drawing the Lewis structures and figuring out what bonds need to be broken or formed, we already know how much energy is required to form many of these things. So let's look at the table on page 424. Okay, so on page 424, there's another table that shows standard enthalpies of formation. So let me move this book over here. So again, I'm on page 424. So here, instead of listing individual bonds, we see molecules or a compound, okay? And this shows, for instance, for CH4 gas, it takes this many kilojoules per mole to form CH4, okay? all of these are given at room temperature, all right? And that's why there's this little degree sign up here, because these values are taken at room temperature, which is 25.0 degrees Celsius. And then this little F notation is saying that this is the standard enthalpy of formation, okay? So to form CH4 gas, it takes negative 74.9 kilojoules per mole, okay? Now remember, these are standard enthalpies of formation. So one thing we can assume is if it takes this enthalpy to form CH4, then to break CH4 apart, it takes positive 74.9 kilojoules per mole, okay? So these values are how much energy it takes to form a compound per mole. If we're breaking the compound down, we just use the opposite sign. Okay, so let's look at, let's just walk through an example of this, and hopefully this will make sense. So I would have page 424 open. Okay. Okay, so let's look at this same equation here. Okay, and actually, so the delta H of formation with this little degree sign, this is delta H of formation. This little degree sign indicates that it's the value at room temperature. Okay. So just so we've looked at this, and again, these values are most commonly given in kilojoule per mole. Okay. So let's start a new sheet. I'll rewrite my equation up here. We have CH4 gas plus we have 2O2 gas yields CO2 gas plus 2 H2O gas. Okay, and we want to know, what's the question asking for? We want to figure out the delta H. Okay, so perhaps an easier way to do it is to use the table on page 424. We can use our standard enthalpies of formation. Okay, so we know we need to break down this molecule. All right, if we look at our table, to create this molecule, and remember we're looking at it in its gaseous form, it's the very first entry on the table. To create this molecule takes negative 74.9 kilojoules per mole. So to break this molecule, we're going to take the opposite of that, 74.9 kilojoule per mole. Okay, and according to this balanced equation, we just have 1 mole of that. Okay, now let's move on to our oxygen. Okay, can we find O2 on the table? O2 gas on the table. Well, it's interesting, the O2 gas isn't on the table. Well, why isn't it on the table? Well, O2 gas is an element. It's how it exists in nature. Okay, so its delta H is actually 0. All right, and if you look at the pink box on page 424, you will see that the delta H of formation of any element in its natural phase is 0 because it doesn't take any energy to create an O2 molecule. That's how it just naturally exists. Okay, so the enthalpy of formation is 0. We have 2 moles of that, not that it really matters. Okay. Now, what's the standard enthalpy of formation for CO2 gas? We look at our table. CO2 gas is in the second column, the second one down. To form it, which we are doing because it's a product, it takes negative 393.5 kilojoules per mole. And how many moles of that do we have? Just one. And then finally we need to look at our water. So we're forming a gaseous water molecule. So that's in the second column at the bottom. Now you'll notice there's two waters. One is its gaseous form, one is its liquid form. So the gas, to form a gaseous water molecule, it takes negative 241.8 kilojoules per mole. And according to our Bounce chemical equation, we have 2 moles. Okay, so here's our equation then for delta H. You'll see in all of this that the moles cancel out. This whole term goes away because of the 0. Here the moles cancel out, and here the moles cancel out. Okay, so our delta H then is, do I have the actual answer down here? Negative 802.2 kilojoules. Okay, so is this an endothermic or an exothermic reaction? Delta H is negative, so it's exothermic. We know it's losing potential energy and gaining kinetic energy, and that by definition makes it exothermic. It's also a combustion equation. You can see that we're adding oxygen, we're getting carbon dioxide and water, so it's the combustion of CH4. Okay, so there we've kind of walked through the nuts and bolts. We can use the standard enthalpies of formation. We take, when we're breaking reactants apart, we use the opposite. We change the sign. So it takes negative 74.9 to form this, but in this case we're not forming it, we're breaking it apart, so we use positive 74.9. Any element in its natural phase, the energy of formation, enthalpy of formation, is 0. It takes no energy to create something in its natural phase. So we can ignore the O2 here. And then in the table we can look up what the standard enthalpy of formation of CO2 gas and of the H2O gas. And then we just add them all up, taking into account when there's more than 1 mole, according to the balanced chemical equation. Okay, so where am I at here on my notes? Okay, so all this leads us to Hess's law. So Hess was a scientist, and he came up with a law that summarizes all of this. Okay, and his law is on the pink box on page 425, and it says for this reaction, where the lowercase letters are the coefficients, the uppercase letters are the molecules, that delta H can be defined as, if we start with the products and take the coefficient times the standard enthalpy of formation of that molecule, plus again the coefficient times the standard enthalpy of formation of that molecule, and then subtract And again, we're subtracting because when we're breaking these down, we need to change the sign. So we subtract the number of moles of A times the standard enthalpy of formation of A. And again, we subtract the number of moles of B times the standard enthalpy of formation of molecule B. So all this is doing is what we did up here. It's starting, this, according to Hess's law, you start with the products and you subtract the reactants. By subtracting the reactants, we're changing the sign on the enthalpies of formation because we're not forming these, we're breaking these apart. Okay? So Hess's law is just a way to write what we did up here. So we basically take the products and subtract the reactants. And when I say take the products, we take the products' enthalpies of formation and subtract the reactants' enthalpies of formation, multiplying them by their coefficients that indicate the number of moles. Okay, so let's see this in action. Let's look at example 14.2. Okay. All right, so 14.2, it wants to know what is the delta H of the decomposition of hydrogen peroxide at 25 degrees Celsius. And it gives us the equation. So we have 2H2O2, and that's in its aqueous phase. It's a decomposition reaction. So it's going to decompose into 2H2O in its liquid phase plus O2 gas. Okay, it tells us this is happening at room temperature, 25 degrees Celsius, so we can easily use our table on page 424 of standard enthalpies of formation. And then when we're done, it wants to know if this is an exothermic or an endothermic reaction. Okay, so to calculate our delta H, we start with the products. So we take the enthalpies of formation of our products and subtract the enthalpies of formation of our reactants. Again, we're subtracting because our table gives us formation enthalpies. Our reactants we're not forming, we're breaking them apart, so we need to take the opposite. And by subtracting, that gives us the opposite. Okay? So our products here, okay, so we have 2 moles of water. And to form water, liquid water, we look at our table. And that is 285.8 kilojoules per mole. My daughter just walked in. Say hi, Emmy. She's home from college because Purdue is canceled all in-person classes. And yes, I'm recording. Okay, sorry for that distraction. Okay, so 2 moles of water. And to form each mole of water, it takes negative 285.8 kilojoules. Okay, are we done with our products? Are we done with our products here? Well, we still have our O2 gas, but our O2 gas, this is how it occurs naturally. It's a diatomic molecule. Okay, so it takes no energy to create O2 gas. Okay, So we could just put a +0 in there for the oxygen. Okay, so this is our water. This piece is our oxygen. Okay, so we're done with our products. Now we're going to subtract our reactants. Well, we have 2 moles of hydrogen peroxide. So H2O2 aqueous. Can we find that in the table? H2O2 aqueous. It's at the very top of the 3rd column. It's minus 191.2 kilojoules per mole. Okay, now notice I did not change the sign to positive. Because I'm subtracting, that by default will change this sign to positive. So when I'm using Hess's law, I just use the values in the table exactly as they are. This negative is going to change this sign to a positive because we're not forming the hydrogen peroxide, but we're breaking it apart. Okay, so this is the hydrogen peroxide. Okay, you'll see here the moles then cancel out. So I'm just left with kilojoules. So if I do this out, I end up with here negative 571.6 kilojoules plus 0. Here's my 0. Minus, well, it's a minus times a minus, so it's actually going to be plus 382.4 kilojoules. Add this all up, I end up with negative 189.2 kilojoules. So this chemical equation takes this much energy to run. Okay? At the very end, it wanted to know, is this exothermic or endothermic? What do you think based on the value you got for delta H? Well, my delta H is negative, therefore it's exothermic. Remember, enthalpy measures how much potential energy. I'm losing potential energy since this is negative. If I'm losing potential energy, that means it's being converted into kinetic energy. And it's an exothermic reaction. Okay, example 14.2 has a second part, exact same thing. It gives us another reaction. It wants us to calculate the delta H. It's at room temperature, so we can use the table on page 424. And then at the end, is it exothermic or endothermic? Okay, so this is part 2 of the same example. The equation is 2 carbon monoxide gas plus 4 water molecules gas yields 2 CH4 gas plus 3 O2 gas. Okay, so here's my balanced chemical equation. I want to calculate delta H. Okay, again, we're going to look at our products first. Okay, so start with the products. Products minus reactants. Okay, I'm gonna have to write a little bit smaller, so hopefully you can see it. Okay, so we're gonna start with our products. Right here, CH4, we have 2 moles. And we're forming CH4 gas. So go to our table. What's the standard enthalpy of formation for CH4 gas? Well, it's our negative 74.9 kilojoule per mole. Okay. This is another product. We have 3 moles. Okay, O2 gas. Again, O2 exists naturally as O2 gas, so its enthalpy of formation is 0. Okay, so we're done with our products. We've taken both of these into account. Now we're going to move to our reactants. We subtract each reactant. So negative 2 moles of CO gas. Well, where's CO gas in the table? It's in the second column, the third one down, minus 110.5 kilojoule per mole. Okay, we have another reactant, so we're going to subtract. For every reactant, we're subtracting. Okay, we have 4 moles H2O gas. So again, you have to make sure you get the right phase. Second column at the bottom, there's 2 H2Os, one's gas, one's liquid. We're going to use the gas. It's negative 241.8 kilojoule per mole. Okay, you can see here all my moles cancel out, and I'm left with just kilojoules. This whole term goes away because it's times 0. Okay, so 2 times the negative 74.9 is negative 149.8 kilojoules. This one goes away. Here I have a negative times a negative, so that turns into a positive 221.0 kilojoules. Again, I have a negative times a negative, so that becomes a positive. The 4 times the 241.8 is 967.2 kilojoules. And if I add all these up, my delta H is 1038.4 kilojoules. Okay, so this is my answer. All right, again, exo or endothermic. Okay, well, my delta H is positive, which means that I'm gaining potential energy. If I'm gaining potential energy, it's an endothermic reaction. Okay, so that takes us up through the middle of page 426. I would like you to actually go well, yeah, that's good. All the way through page 426. So you'll just have, in this coming week, you will have the test for chapter 13. What else will you have? You'll start chapter 14, going up through comprehension check number 4. It's going to be critical that you read the book, work through all the problems, try to understand what's going on. In addition to the comprehension checks, I am going to assign some of the review questions as well, just as extra reinforcement for what we're doing. So yeah, that's all we have this week. Chapter 14 will be split up into 3 parts. We've just done part 1. So I hope you have a great week. If you have specific questions that you think others might benefit from, please put them out on Google Classroom. If something individual that you want to ask, you can always text or call or email me. So have a good week, and we'll talk to you soon.